Hello everybody, it's me again with the installment number 6 of this summer term's lecture on Adaptive Mesh Refinement. So 29 page is just there because I had forgotten to write X and L here. This is a typo that has been fixed in the latest PDF files that are uploaded. This was already done the lecture before, and where we began this week was page 31 with a brief review of all the element algorithms that we had already. We fix some maximum level big L for practical purposes that we cannot exceed, but what this is going to be is of course up to you if you choose to program this, and then all coordinates are integer steps in this range from 0 to 2 to the big L exclusive for each dimension, x, y, z, and so on separately. So we had discussed function for validity of an XL pair, coordinates and level that make an element a valid refined element. So it's a child of a child of a child and so on of the root element. Not all possible values for x and L are legal in this construction, or more specifically do not identify some descendant of the root element. The root element itself is just the pair 0, 0. We can construct a child with a number j here, and we can go up to the parent, which the child, for example, will increase the level by L and the parent will decrease the level. Siblings are same level children of the same parent, and of those we have 2 to the power of d many, since they are all children, so we can index the sibling function with the same parameter j here, and this will produce something like this. Of course, this is a bit of a clumsy expression just to show the logic of it. It can be constructed more efficiently by using bitwise operations. What's new? This is supposed to be just a vertical bar down here, which I'm understanding as bitwise OR. So each bit of the left and right operand is bitwise OR together to produce the bit of the result. And we do this only if j is even in the direction. So j logically ended with the power of 2 gives the 1 or 0 status of the bit number I counted from the right 0 based. So if this is 0, then j is even in that direction. If it's 2 to the power of I, it's odd, and for even we just stay left, and for odd we go right if it's the x dimension. Otherwise we stay down and go up, or we stay front and go back, and so on. If we stay left, we would I'm sorry, I pointed the wrong way around, right? So if we are odd, then this is true, and we go here, so we're potentially adding, meaning moving a coordinate to the right, to my right. This video is made up in a way that my right is your left, as we would just be seeing each other in class, right? So, and this is the case for even, where we would actually possibly decrease the index since we are removing one of the bits if we're going into this branch. Okay, so children are direct descendants, parents are direct ancestors. Of course, we can repeat this or iterate. And then we have indirect descendants and ancestors. I will not go into detail here. It's equivalent to just doing parent multiple times, beginning with a level L element and stopping with the level L prime element. So L prime must be less equal L to make the element bigger, going up the tree. And we do this by just bumping the element into the lower left corner of its parent, basically removing all the bits that make it multiples of a fine-grained coordinate axis and making it a multiple of a coarse-grained coordinate axis that corresponds to the parent, and this means moving it towards the origin to allow the parent to encompass the original element, since that's what an ancestor is. It is surrounding any of the children and recursive children. So you can go through this picture here, And of course, we have another couple of algorithms that we always need. Equality is near trivial here. Descendants going all the way down to a certain level L prime, in this case L prime would be bigger than the original level, bigger or equal. This really means we're going down into the bottom left corner by making the element smaller, so all we're changing is L to L prime, and X stays the same. But of course, if we take the highest possible child, we're increasing the coordinates of X and move it into the top right corner of its ancestor. And this we do by adding this length of the big element and removing the length of the small one, h of L being just the size or the length of one dimension of the element in integer coordinates. So if you think about this, this is quite natural. It is coordinate wise. So you might want to prove, for example, that first and last descendant are still valid if applied to a valid input element. Should not be too difficult. So if we want to know if one element is the ancestor of another, it means that the smaller element of the two must be inside. So it cannot be left and it cannot be right, which means that the prefix of the bit string to the high bits must be the same. Otherwise, we would be moving left or right in multiples of the parent size, and then we would not have an ancestor, we would have unrelated elements. Two elements being unrelated is equivalent to not one of them being equal or an ancestor of the other. So this is the function. If you see that, of course, we require that the level of the ancestor would be less equal than the level of the descendant. Otherwise, this cannot be true, and then we check the coordinates for having the same prefix up to for all the high bits above level L. We do this by exclusive OR operation, this can be used to prove that its ancestor is transitive, which makes sense since descending to some intermediate element and descending further is just can just be concatenated into descending all the way in one go, right? So this is the property 312 here. I mentioned this convention here that logical operators in the C language are short circuit evaluated, which means if A is false and we do an AND, then the condition cannot be true. The result cannot be true, and we will never evaluate B. Same for logical OR. So the operators are commutative, but the evaluation of the second argument is depending on the value of the first argument. So this is very important to know. This is done in C and in Python and many other languages. As a side note here. In practice, this means if this comparison with L and L prime is false, we will never evaluate this more expensive expression and just return false as a whole, which makes perfect sense. I'm not going to the proof. I really recommend that you do this. I'm using some just basic algebra on exclusive OR here. So I'm curious if you like this or if you would have done this differently or maybe even quicker than I can do it here. And I will close for today with another function to find the nearest common ancestor of two elements. This is also quite intuitive. If I have two elements, then I go up the tree as much as I need for both having the same ancestor. So the level must be bigger than the maximum of either input levels, bigger equal actually, and how far we go up depends on the differences in bits depending on the position. So this is something that I am not explaining very well here. Maybe I'll come back to this later, but possibly you can just think about how would you define the function nearest common ancestor. Input are two quadrants, xl and x prime l prime, and you get one result that is an ancestor of either that is the same one. So thanks up to here. I hope you're enjoying your programming with some of those element local functions, and from the next session on we can actually start combining those calls into algorithms that actually create a mesh that is made up of not just one element but many elements that are all together spanning the domain. So thanks, and I'll talk to you soon.